Joe DeLee. I'm the director of the mass spectrometry laboratory in the Department of Chemistry. And Pete asked me to give a couple of lectures on mass spectrometry, specifically liquid chromatography, mass spectrometry, and with a detailed discussion of quantitation using LCMS. So on Wednesday, I will get into a detailed lecture on quantitation, but before we do that, there's a whole suite of different mass analyzers one can put at the back end of separation techniques such as liquid chromatography or gas chromatography. And I want to give an overview to understand the choices one makes when you decide to do quantitative LCMS. This is my email address for your 1-minute papers. So you can email your 1-minute papers to me after the lecture today to this address. Or if you have any questions on the lecture, feel free to email me as well. I want to start, and I won't go into much detail with this at all, because I'm sure Pete and the other professors who are teaching this course are going to go into a lot of detail on HPLC and gas chromatography. I'll talk about the different ionization techniques with mass spectrometry, as well as the different types of mass analyzers, and what the strengths and the weaknesses are for each of those, especially in the context of doing quantitative analysis. And then basically when you combine LC with mass spectrometry, many of the factors involved are going to be similar to combining GC with MS, other than types of modal phase selection and so forth that's going to be specific to LCMS. And then we'll talk a little bit about applications of LCMS. Rather than going into a lot of detail talking about HPLC, which I'm sure you're all getting a very strong background in this, I think it's very interesting. If you get into a field where you begin doing separation science in combination with mass spectrometry, what you'll see and what you will hear at meetings is somewhat of a playful battle between the two teams, basically. One will be the separation scientists and people that do advanced liquid chromatography and advanced GC and other separation techniques, basically discussing mass spectrometry and a mass spectrometer as if it's just a detector for doing separation science. And on the flip side of that coin, mass spectrometrists will, in a tongue-in-cheek way, discuss chromatography as just an inlet for doing mass spectrometry. So you'll hear both of these on, and there's always the pro-mass spec crowd and the pro-liquid chromatography crowd. But the fact is they're both incredibly powerful techniques for doing separations and finding needles in a haystack, going into a complex biological, food, environmental matrix, and being able to separate out what it is you want to see or unknowns and then characterize them in some way. And mass spectrometry really can be thought of as a separation technique. It's completely orthogonal to liquid chromatography or gas chromatography, but you're just doing a separation based on mass to charge ratio and the unique mass of the given compounds you wish to analyze. And you can do that in 1 or 2 dimensions. You can detect the mass to charge ratio of a given compound in 1 dimension and get a peak every time you detect that specific mass to charge ratio. Or you can do tandem mass spectrometry, where you use a first mass analyzer as a filter, let that parent mass to charge ratio through, and then fragment it in a second section of the mass spectrometer, break that into fragment ions from the precursor ion, and then use your detector to detect those fragment ions that are specific to the precursor, such that you get a 2-dimensional separation, basically, based on the unique mass to charge ratio of the precursor ion, as well as the unique mass to charge ratio of the daughters. One thing I do want to mention in terms of liquid chromatography is the advent of ultra-performance liquid chromatography in the past 4 or 5 years. And this is basically an engineering development where there are now commercially available liquid chromatographs that have been engineered to withstand back pressures to 12 to 14,000 psi, compared to 5 or 6,000 psi for a standard liquid chromatograph. What that has allowed is, in a commercial, sort of user-friendly benchtop liquid chromatography system, to go to higher flow rates. You can go to smaller particle columns, which generate higher back pressures, but also give you higher resolution and more rapid separations over a shorter time frame. Such that here is a chromatographic separation of polyphenols in green tea, shown on a standard liquid chromatograph. These have diastereomeric pairs, which have the exact same mass, so liquid chromatographic separation is required. And in order to get separation of those diastereomeric pairs, 1 and 2, 4 and 5, by standard LC, you're looking at a 15 to 40 minute separation. If you go to UPLC, you can go to smaller particle size within your columns. You can go to higher flow rates, and you can affect similar separations of these diastereomeric pairs in the entire suite of polyphenols in a mixture such as green tea within 3 to 4 minutes. So it accelerates your separations, it accelerates your detection, it accelerates your entire experimental protocol, because you can now analyze 100 samples a day instead of 10 samples a day. Further your research in a more rapid fashion. So what I'd like to do is just give a general overview of mass spectrometry. And there are basically two main things that are going to vary when you talk about mass spectrometry at the back end of chromatography or other separation techniques. And that's the ionization technique and the type of mass analyzer you're going to use. So just in sort of a white box diagram, what you have with a single mass analyzer mass spec is some ionization source where you're going to take the effluent off of an LC, and you're going to get those analytes into the gas phase with a specific mass to charge ratio. Those analytes of specific mass to charge ratios in a mixture will then be separated using a mass analyzer, and then they'll hit the detector, which will give some detector response, and you then get a plot of intensity of that given mass to charge ratio versus the mass to charge ratio itself. You can also have dual mass analyzer mass specs. So if you hear tandem mass spectrometry or MSMS, what you have is an ionization source followed by a mass analyzer to separate out the precursor ions that are formed in the gas phase. You then use a second compartment within the mass spec as a collision cell. You can introduce argon or helium or nitrogen or some other neutral gas at some specific flow. It will collide with the ions formed in the ionization source, break them into pieces, and then you can use the second mass analyzer in the mass spec to separate out those fragment ions and go and hit the detector and get a mass spectrum that way. That becomes very important when you begin to think about doing quantitation and detection in very complex mixtures, because now you can really look at a dual mass analyzer mass spec like this as a two-dimensional separation instrument, where you're separating based on the unique mass of a parent and a fragment ion specific to a given compound. So if you need to go into a complex mixture, pull a needle out of a haystack, and you can do it with 2 dimensions of mass selectivity. LCMS MS becomes very powerful. The types of ionization techniques at the front end of mass specs vary widely, and they vary over the course of history. Initially, most ionization techniques for mass spectrometry were vacuum ionization techniques, meaning ions were formed in the gas phase under high vacuum. So things like electron ionization, where you're exposing your sample to 70 electron volt electrons. Very hard ionization technique. It makes the ions go into the gas phase, and it fragments them quite a bit. This is the type of mass analyzer, you will have usually at the front end, or of a GCMS instrument, you'll get an electron ionization mass spectrum, which fragments the compound of interest pretty extensively. But that fingerprint, because all GCMS instruments are exposing these samples to 70 electron volt electrons, the mass spectrometers are very similar in configuration. Those fragmentation fingerprints in EI become very characteristic of the analytes that you're detecting, such that you can develop very powerful databases. So you go to a NIST database or a Wiley database, and they have PLC, where you have a high pressure, high flow eluent coming off of a chromatograph. Vacuum ionization techniques are not going to be compatible. You can't have a high pressure flow going into an ionization compartment that's under high vacuum. So you're not going to see LCEI or LCCI, but you will see GCEI and GCCI. Matrix-assisted laser desorption ionization. Basically there, what you're doing, and it's all under vacuum, you're spotting a sample on a stainless steel plate, and you're adding a UV absorbing matrix to that sample. You put it into the vacuum chamber of a multi-mass spectrometer, you hit it with a UV laser, the matrix absorbs that UV energy, transfers it to the compound at that spot, and desorbs the compounds into the gas phase, where they can be separated in the mass analyzer and you can detect them. A very soft ionization technique forms primarily singly protonated ions, and very powerful for intact proteins, polymer analysis, things like that, where you just need a quick and dirty analysis. You can spot 120 samples on a stainless steel plate. It takes you a few seconds to get some mass spectra for each one of those places. So you aren't doing any separation here. Things need to be reasonably pure, that you can do some rapid mass spec for verification purposes on synthetic or biopolymers. Fast atom bombardment is finally one other vacuum ionization technique. Again, it's soft ionization. You're using a stream of cesium ions to sputter ions from a sample that's dissolved in glycerol or some other matrix. Again, this takes place under high vacuum, so FAB, as it's called, is not very compatible with separations at the front end. In 1989, a man named John Fenn, who was at Princeton, developed Electrospray ionization for mass spectrometry. And he later won the Nobel Prize for this because it really revolutionized bioanalytical mass spectrometry and allowed for the first time very routine, directly combined liquid chromatography mass spectrometry. And the reason for this is that electrospray ionization represents a technique that relies on a flowing stream of liquid from an infusion pump or the eluent right off of an LC to form ions. So it's perfectly compatible with liquid chromatography. This flowing stream of liquid goes through a stainless steel capillary that's held at a potential, either negative or positive, with respect to the entrance to the mass spec of about 3,000 volts. As this flowing stream of liquid goes through the electrospray capillary, these solvent droplets containing analytes become highly charged. There's a flowing stream of hot nitrogen coming over the top of this capillary. This ionization chamber, which is under atmospheric pressure, is also heated so that these droplets begin to desolvate and begin to evaporate. As they evaporate into smaller and smaller droplets, the charge density on those droplets becomes higher and higher until you get to a point where the electrostatic, the Coulombic forces of those charged particles within the droplet overcome the surface tension of the droplet. The ions explode into the gas phase and then can enter the mass spec, be separated and detected. There are a couple other atmospheric pressure ionization techniques of note. One is atmospheric pressure chemical ionization, very similar to electrospray, except what you're doing there is that in the source of the mass spec you have a corona pin that discharges, and it charges the solvent within the mass spec source, and you get charge transfer similar to chemical ionization in a vacuum ionization technique, and charge transfer, primarily singly charged compounds in APCI, such that the molecular weight range for APCI is a little lower. I forgot to mention in electrospray ionization, the other thing that really revolutionized bioanalytical chemistry is that in electrospray ionization, you can the process puts multiple charges onto analytes. So you can have a protein of 10,000 molecular weight and have a mass analyzer that only has a mass to charge range of 2,000. But if you put 10 charges on that protein of 1,000 molecular weight, now you have a mass to charge ratio of 100, and you're able to detect large peptides, proteins, things like that, using standard mass analyzers, because you can have multiple charges on these analytes, like large DNAs, RNAs, proteins. So now, while electrospray is limited to more polar, non-volatile type compounds, the molecular weight range is from 50 up to 100,000, because a mass spectrometer is measuring mass to charge ratio, not mass. So if you can put a lot of charges into a compound with lots of basic sites like a protein, then you can bring that mass to charge ratio down to the point where you can measure accurately the molecular weights of compounds, up to 100,000 molecular weight. Atmospheric pressure photoionization is very similar to APCI, but you can get a little further down into the non-polar range. And basically, you're just using light to affect ionization of compounds. So now what I want to do is talk about the different types of mass analyzers. And the reason I want to give an overview of that is that on Wednesday, when we begin to discuss how you do quantitation, how you do separations in complex mixtures to quantify compounds, in those complex mixtures, choice of mass analyzer is going to be important. And so I want to give you sort of an overview of a whole suite of different mass analyzers that are out there, what their advantages and disadvantages are, especially from the standpoint of doing quantitative analysis. First mass analyzer I want to talk about is really the most simple. It's called a quadrupole mass analyzer. You will hear talk of mass specs as being single quads or triple quads, and we'll talk about that in a little more. If you have a single mass analyzer, mass spec with a quadrupole, it can be called a single quad. If you have two of them in series, actually three in series, one of which will be used as the collision cell for LCMS, it will be called a triple quad. What a quadrupole mass analyzer is basically four rods in parallel within the mass analyzer, two of which you will apply a DC voltage and two of which you'll apply a radio frequency voltage. You then scan the RF voltage such that at any given RF frequency, only ions of a given mass to charge ratio will have a path through the quadrupole and be able to hit the detector. So you'll then get a plot of RF frequency versus intensity of those peaks hitting the detector, and that RF frequency can be calibrated and translated to the mass to charge scale, such that you get a mass spectrum of mass to charge ratio versus the intensity of those masses hitting the detector. You can set these up to scan RF voltage, to do a full scan from say 50 M over Z up to 1500 M over Z, or you can set a quadrupole up basically as a mass filter to say, I only want M over Z 459 to go through that detector because I have a known component that I want to detect and quantify. I don't want to see anything else. And you can set these up as a mass filter to only see a peak when your peak of interest comes through and hits the detector. Ion traps and FTICR mass analyzers. Ion traps are basically quadrupoles, but the quadrupoles are set up as a trap. So you can have a combination of DC and RF voltages on those quadrupoles where you're trapping ions of specific mass to charge ratio or a range of mass to charge ratio, and then selectively eject those ions to hit a detector over some amount of time. The advantages of trapping are sensitivity. You can accumulate ions over time. There's also the advantage of being able to do what's called MS to the N, meaning you can have a precursor ion of a specific mass to charge ratio introduce argon or helium, fragment that into pieces, trap those pieces, and then you could fragment those pieces again, so you could do NS to the third or NS to the fourth and get more structural information on a specific FTICR is basically another type of trapping instrument. What you're doing here is you're injecting packets of ions into a region that is under the influence of a magnetic field. Now, ions of a given mass to charge ratio will begin to precess perpendicular to that magnetic field, and that precession frequency charge ratio will begin to precess in this magnetic field. They begin to separate out based on their resonance frequencies with the magnetic field. As they're doing that, and as energy is introduced into the ICR, the radius of those orbits becomes wider and wider until it hits the edges of the FTICR cell, which causes an electrical signal that's proportional to the abundance of that ion within the cell, and then you can measure the mass to charge ratio. I have a movie of FTICR, which will watch, give you a better picture of how this works. And it'll sort of show you ionization through mass analysis in a nice little illustration. So here you've got your electrospray needle at 2 kV. You're forming those charged droplets, which are evaporating when the surface tension of the charge within that, or when the coulombic forces overcome the surface tension, you get the naked ions. They enter the mass spec, which is held at a potential compared to the electrospray capillary. They'll go through a number of focusing quadrupoles and hexapoles and things like that into distinct packets of ions. Those packets of ions are then transmitted into the FTICR cell, or ICR cell. So if we now look at this on end, now this ICR cell is under the influence of a magnetic field. And all of those ions have unique mass to charge ratios, so the frequency of their precession is individual and dependent on their mass to charge ratio. So as you do this, they begin to separate based on their mass to charge ratio, based on their resonant frequency, and you get an infinite number of sine and cosine waves that represents the wave functions of all the different ions within that ICR cell. You can then do a Fourier transform on that infinite set of sine and cosine waves and get a mass spectrum of amplitude versus frequency, and then because their resonant frequency is proportional to their mass to charge ratio, you can translate this amplitude versus frequency spectrum into an amplitude versus mass to charge ratio spectrum. And because frequency is very easy to measure, and you can measure frequencies very, very accurately using modern instrumentation, FTICR is the most accurate mass spec you can use in terms of determining mass accuracy. It's the highest resolution because you're spending a lot of time letting these things precess at their unique frequency. You're getting incredibly good separation between two compounds with very similar mass to charge ratios. And you can also, therefore, because you have such high resolution, get very high mass accuracy. The disadvantage of trapping technologies, especially from the standpoint of doing directly combined LCMS, is that the duty cycle is very low. You're spending a lot of time either with an ion trap, trapping those ions within the cell and separating them out, or as you saw with an FTICR, there's a certain amount of time involved in letting those process and separate. The problem with that is if you have high efficiency separations, either GC or LC, where you have a good chromatographic peak that's only a second wide, and your duty cycle on your mass spec is one mass spectrum every 3 seconds, you're not going to get a lot of points across the peak. You're not going to have a nice Gaussian detection peak. You're not going to be able to do as accurate a quantitation. Another type of mass analyzer is a time-of-flight mass analyzer. Very high mass accuracy and very high resolution. Not as high mass accuracy or as high resolution as FTICR, but you have a much more rapid duty cycle. You can get full scan mass spectra at about 20 hertz, or 20 scans per second, which is very compatible with high efficiency separations. Basically what you're doing with the time-of-flight mass analyzer is you're taking a packet of ions and pushing them all with a given specific kinetic energy. And if all of the mass to charge, all of the ions of different mass to charge ratios have similar kinetic energies, the smaller mass to charge compounds with smaller mass to charge ratio will reach the detector first. Those with higher mass to charge ratio will reach the detector more slowly, and you can calibrate that time of flight to reach the detector to mass, and you get a mass spectrum based on the time of flight of those ions through the detector. A powerful configuration of mass spec for doing separation science and discovery work is a Q-time. So now we have a quadrupole at the front end of our instrument where we can that we can use as a specific mass filter to only allow through precursor ions of interest. And then go to a collision cell, break that into pieces, and get high mass accuracy measurements of analytes using the time-of-flight mass analyzer. So similar to a triple quad in terms of what you can do, and being able to do LCMS and MSMS, but high mass accuracy, both for the precursor ions and for the daughter ions. The disadvantage of time of flight versus quadrupole mass analyzers for doing quantitation is that you have a smaller linear dynamic range of response for the detectors that need to be used with time of flight instrumentation. Therefore, doing quantitation over a wide range of concentrations from very low to very high and having that dynamic range for quantitation is not as good with the time of flight instrument as it is for a quadrupole, but it's getting better. This is a summary, and I will submit my my lecture notes to Pete so that you guys can access this. I won't go through it in a lot of detail now, but it's a nice summary of the different types of mass analyzers, resolution characteristics, mass to charge range for each scan speed, can you do tandem MS, and its compatibility with LCMS. And I'll focus on that for now as a lead-in to our lecture on Wednesday when we'll talk about LCMS quantitation. Quadrupoles, as I said, very compatible with LCMS because they have a good mass to charge range. They're very high duty cycle. You can get a mass spectrum every 0.1 second or lower. When you're doing MSMS, you can get to 100 per second, which means you're going to get a really nice peak shape. The more detection points you have across the peak, the better peak shape you have and the more accurate quantitation. It also has, it has a high duty cycle. It's compatible with very sharp peaks. And it also has a wide dynamic range for detection. So quadrupoles are very linear mass analyzers over a wide dynamic range, making them very compatible for doing LCMS and for doing quantitation. Traps and FTMS, lower duty cycle, makes LCMS a little more of a challenge because you're not getting a lot of detection points across a chromatography. Time of flight mass analyzers by themselves are very compatible with liquid chromatography, but TOF by itself you can't do MSMS, but if you put a quadrupole at the front of a time of flight instrument, you can do MSMS with accurate. Magnetic sectors obviously are incompatible with LCMS because the magnetic sector instruments, the front end, the ionization techniques that are compatible with those are vacuum ionization techniques. Why would you want high resolution? FTICR mass specs, time-of-flight mass analyzers that I spoke about that were high resolution techniques, high mass accuracy. Why do you want that in MS mode or MSMS mode? It's really for discovery purposes. You want to detect. You don't need incredibly high mass accuracy. But if you're doing discovery where you're trying to identify unknown compounds in a mixture, high resolution allows more accurate mass determination. An example of this is shown here. If we had a putative compound, epigallocatechin gallate here, with an elemental composition of C22H18O11, the exact mass of the M plus H plus ion is 459.09217. If you use a mass analyzer that is accurate to within 0.1 Dalton, this would be similar to a quadruple mass analyzer. You get accuracies down to about 0.1 Dalton. And you go and do a mass, a database search on an M plus H plus ion that's 459.1 plus or minus 0.1, you'll get over 200 hits of compounds containing carbon, hydrogen, oxygen, and nitrogen for something measured with that level of mass accuracy. If you can go to 0.01 Daltons, so you can measure this to 459.09, you can get that down to 39 potential elemental compositions. If you go to 0.001, got a misprint here, it brings it down to 3. And if you can measure this out to a fourth decimal place, which a well-calibrated time-of-flight instrument can do, FTICR definitely can do. Now you go and do a database search on 459.0922, and there's only one possible elemental composition containing those 4 elements. It gives that, and it's that compound. So when you're doing searches on unknowns using these types of mass spec, that's what high resolution and high mass accuracy buys you. GCMS I spoke about a little bit, and the power of doing EI mass spectra using GCMS is that you get these fragmentation patterns and fingerprint mass spectra by EI of different compounds that are very characteristic of that compound. You can then do database searches with Wiley or NISP and get identifications of unknowns based on that very unique. With LCMS, using Electrospray, whether it's a quadrupole, time-of-flight, the mass spectra you get are very dependent on the source design of the manufacturer. They're very dependent on the analyzer design of the manufacturer, such that the mass spectra you get are not well standardized. So doing database searching on LCMS spectra similar to doing on GCMS spectra really isn't possible. Can you do database searches based on accurate mass? Yes, but it's much more involved, and depending on your mass accuracy, you'll have varying levels of success. I want to touch briefly on the LCMS source interface when you want to combine liquid chromatography with mass spectrometry via Electrospray. It's pretty simple. Your inlet or your outlet from your HPLC is coming in to a fitting here where your LC flow is coming directly into an Electrospray source. This is with the door open. You've got this stainless steel capillary that I showed you before, held at a potential. You form your charged droplets, you desolvate those droplets. The ions go into the source of the mass spectrometer right here. From here on back is held under high vacuum. That's where you have your quadrupoles, your mass analyzers, and your detectors for different detection. When you're combining liquid chromatography with mass spectrometry, there are some issues of solvent chemistry that you need to account for, and it somewhat limits the choices of chromatographic systems you can use at the front end. All of your solvents need to be volatile, because if they aren't, or you have non-volatile salts in your mobile phases for chromatography, those are going to precipitate out on the source of the mass spec, they're going to muck it up. You're not going to be able to use it for very long before it's completely contaminated. So your solvents usually are going to be water, methanol, ethanol, isopropyl alcohol, acetonitrile, acetone, things like this that are very volatile. Your acid and base modifiers need to be volatile: formic acid, acetic acid, trifluoroacetic acid, ammonium hydroxide, ammonium bicarbonate, ammonium. Salts or buffer additives, you can add ammonium formate or ammonium acetate. So that's it's not an exclusive list. There are other things you can try, but 98% of every LCMS separation you'll see out in the literature is going to be water, reverse phase chromatography with a gradient from high water to high acetonitrile containing 0.1% formic acid. And that'll be most of the separations you're going to see when using mass spectrometry. And people will sacrifice chromatographic performance because they have this high dimensionality separation based on unique mass using the mass spec. That's not to say you don't get certain applications where you absolutely have to spend a ton of time developing a great chromatographic method when you're separating isomers. You can do normal phase chromatography at the front end of mass spec, but the same solvent considerations need to be made. Reverse phase chromatography is going to be the most standard, where you've got a C18 phase. Your more hydrophobic compounds are going to be retained longer, and you're usually going to run a gradient from high aqueous to high organic to alert those things on in specific packets, and then couple to the mass spec. Finally, I just want to talk about some of the different mass spec experiments you can do when combining with liquid chromatography. There's a lot of different ways you can set up the mass spec detector to get different types of information from your separation and detection of whatever system it is you're studying. The first and most straightforward, and what I'm going to do is use a triple quadrupole mass spec as a model for talking about these things. Most of the experiments I'm talking about here you can do with other dual mass analyzers as well, like a quadrupole Timeofflight. You can do everything we do here with a QTOF, with one exception that I'll discuss that you can with the triple quad. But we'll talk about this from the standpoint of using the triple quadrupole mass spec. First and most simple is a full scan, where you're going to scan over a mass to charge range from say 50 to 1500. Detect as many components as possible in that window. And what you're doing there is you're scanning your RF on your first quadrupole, forming your ions, letting all of those ions pass through. You've got your collision cell opened up. You're not introducing anything in here to break it into pieces. And you've got your mass analyzer 2 opened up. So you're basically only using this as a single quad. Form ions, separate out by scanning RF, hit detector, get mass spectrum. What you get with a complex mixture, this is a soy extract. You do an extract on soybeans, you dilute it, you inject it onto your liquid chromatograph and do mass spectrometry at the back end, scanning from say 100 to 1500. This is a total ion chromatograph. Every time any ion of any mass to charge ratio hits the detector, you get a peak. Very complex, but if you're interested in finding something of a specific mass to charge ratio in here, you can use the software on the mass spec to go in and do what's called a selected ion chromatograph. So from this mess, you could go in and say, I wonder if there's glucose here, show me M over Z 179. And only when M/Z179 hits the detector, and you'll get this selected ion chromatogram where, boom, glucose hits right there at 2 minutes, and you've detected glucose in a very complex mixture. So even though this looks very complicated, you can go in and sort of pull the needles away from the haystack if you know what it is you're looking for. You can take the selected ion chromatogram and turn that into an actual MS experiment by just doing what's called selected ion recording. So if you have one specific compound you're looking for, we want to see 2,3-phosphoglycerate in a cell extract. This is a glycolytic intermediate from glycolysis. We form our ions on the cell extract. We set up both mass analyzer 1 and mass analyzer 2 as mass-specific filters. So we say only allow through M/Z 185 for 2,3-phosphoglycerate 2 here. So you set your RF frequency and your DC voltage such that only M/Z 185 can get through. Everything else hits the walls of the mass analyzer. Open up your collision cell. 2 filters set to transmit only ions of one specific mass-to-charge ratio, and you only get a peak for that mass-to-charge ratio you want. You can set up an experiment where you have several selected ion recordings simultaneously so that you're not limited to just one analyte per room. And you can look at each of those individual channels separately. The advantage of selected ion recording over doing selected ion chromatograms on a full scan is sensitivity, because your detector is sitting there and ions of one mass to charge the entire experiment. You're not missing M/Z 459 while M/Z 850 is being transmitted through the quadrupole. You can take selected ion recording and do it in 2 dimensions to add 2 dimensions of mass selectivity for a specific compound. This becomes very powerful, and it's really the method of technique for doing quantitative LCMS. You're forming your ions, you're setting up your first quadrupole as a mass filter to only filter through the mass-to-charge ratio of the precursor ion of the compound you're interested in. So if we look at the 2,3-phosphoglycerate example, we're going to set up the first quadrupole to only transmit M/Z 185. You then open up your collision cell and introduce argon or helium or xenon, break this ion into pieces, and those fragments are specific to the parent ion of interest. You can determine this in an initial experiment where you take a standard of 2,3-phosphoglycerate, you introduce it to your mass spec, you break it into pieces, and you make note of all of the fragment ions that are specific to the precursor or parent ion for 2,3-phosphoglycerate. So you set this up as a mass filter for the parent, break it into pieces, set up Q3 as a filter for a fragment ion that's specific to that parent. Now you have 2 dimensions of mass selectivity for a given compound. The odds of some other compound in a mixture, however complex, of having the same exact precursor mass-to-charge ratio and product mass-to-charge ratio are very low, such that you've got an incredibly selective detection format for going in and finding one analyte in a very complex mixture. Constant neutral loss is an interesting experiment if you're looking for a suite or a family of compounds, all of which have similar structural characteristics, all of which will form similar fragment ions because they're losing a specific chemical moiety from the parent ion, you can set it up to detect all of the components in a mixture that do that. A good example might be phosphorylation. Let's say you have a tryptic digest of a protein and you have a complex mixture of peptides. And you want to identify all the peptides that are phosphorylated. Loss of a phosphate group as a neutral loss from a phosphorylated peptide is a very common fragment. So what you're basically telling the mass spec is, show me every time there's a precursor ion that loses 80 when we introduce it into the collision cell, or loses a phosphate group when we introduce it into the collision cell. And you'll only get peaks for compounds that are phosphorylated. The way you do this instrumentally is you're scanning RF or DC in your first quadrupole, similar to what you do for a full scan experiment. You're opening up the collision cell and you're opening up that to xenon or argon so that you're breaking everything that's going through here into pieces. Simultaneous to scanning RF or DC in your first quadrupole, you're scanning your RF or DC at an offset that corresponds to that constant neutral loss. So as this is scanning through M/Z 480, we have this at the same time only allowing to pass through M over Z 400 for a loss of 80, such that you only get a peak hitting your detector, you only get ions hitting your detector when you have something here that's having a constant neutral loss of 80 Daltons in your collision cell. So you're only going to see things that are phosphorylated. You can do that for glycosylation, any sort of chemical modification you're interested in, and you want to see the full family of compounds that may experience that. Daughter scans, this is what you would set up prior to doing a multiple reaction monitoring that I talked about. The multiple reaction monitoring was setting up this to filter only the parent, breaking it into pieces, and setting this up to only transmit a fragment ion specific to that parent. The experiment you'd do before that would be a daughter scan, where you're filtering a single M over Z, breaking it into pieces, and then you're scanning this third quadrupole to get a full mass spectrum showing the fragments of that compound. You can then pick one of the high intensity daughter ions, say 139, and now you can make an MRM experiment where you're only going to monitor this 459 to 139 precursor to fragment transition. Finally, a parent scan. Sometimes it may be of interest. You'll get a mass spectrum. Very seldom are they really simple, where you only see a single peak under, say, a single liquid chromatography. You may have a chromatographic peak coming off like this. You average the mass spectra underneath that specific chromatographic peak, and you get a number of peaks at different M over Z ratios or values. Let's say this mass to charge ratio is very interesting. It's 159. It's interesting only if the parent compound has a mass of 159. If 159 happens to be a fragment, which you get within the ionization source, you can still get fragmentation of these things without going through a collision cell. You don't want to get fooled and report that you've detected some parent compound of mass 158 with an M over Z of 159 if this happens to be a fragment of something at M over Z 330. What you can do to prove that that's not a fragment is you could do a parent scan of M over Z 159. So you're only allowing through 159 here. But if this is a result of fragmentation of something that was going through here, wherever this was scanning at RF when 159 saw the detector, it knows that, and it'll tell you the parent M over Z value for that fragment ion. So you're forming your ions, you're scanning RF here, letting everything through, breaking everything into pieces, but only allowing through one specific daughter ion. So if 159 happens to be a daughter, you set this up for 159. When that hits, if this is at 159, that's the parent. It's not a fragment. But if you get a peak here for this M over Z 159, and it resulted from when this was allowing through M over Z 459, then you know this is a fragment ion of 459 and not an intact compound that you're interested in. Does that make sense? Finally, all of these experiments, particularly MSMS, like MRM experiments, can be used for quantitation, where you make up a set of standards and you look at the response within the mass spec versus the concentration, form a calibration curve, take your unknowns, run them, quantify them. And that's what we're going to talk about on Wednesday. There's a lot of really special considerations one needs to make when you're doing LCMS quantitation, and we'll talk about those, some of the challenges and some of the things you need to do to be able to do it accurately. Any questions? Otherwise, you can send questions or anything else to me, my email in your 1-minute paper.